All right, in our last video, we discussed the theory behind Lagrange multipliers. In this video, we're going to work through a few simple examples of how they can be applied to find maximums and minimums of the intersections between functions. Before we get started, if anything that we go over today is helpful to you at all, please leave a like and consider leaving a comment if there's anything that you would like me to go over next, or if there's any improvements that I can make to my videos, as I put quite a bit of effort into them. All right, hope you enjoyed the video. Let's get into it. All right, for our first problem, we're going to maximize the function z equals x times y for the constraint x plus y equals 10. All right, now let's specify our functions for the cost function and for the constraint function. So the cost function is just this one right up here. Now let's go ahead and change to blue for that. All right, this one right up here. And z is just a function of x and y, so f of x, y equals x times y. All right, now for our constraint function, we're going to call that g of x, y is equal to x plus y is equal to 10. Now, what we did there was we put the constant in here as well, because that's also part of our constraint equation in this case. We're going to need that when we go to solve for our x and y values when we're finding our critical points. All right. So how do we find those critical points? Well, if you remember from the previous video, we use the Lagrange formula, which looks like this. We have the gradient of our f function is equal to lambda multiplied by the gradient of our g function. And this will result in a system of equations once we figure it out. That's going to give us our different values. So let's go and figure out these gradients, shall we? Okay. So the gradient of f of xy is equal to, well, it's a vector with two components, right? Because it's a function of two components. So the first component is going to be the partial derivative of f with respect to x, which is just y. And then the second component is going to be the partial derivative of f with respect to y, which is just x in this case. All right, now let's figure out what the gradient function of g is. That's also a vector, and its components are partial derivatives of their respective variables as well. So the first one is a partial derivative of x, which is just 1 in this case. And then the second one is partial derivative of y, which is also just 1. All right, so now we have our two different gradient functions, but what do we do with them? Well, we take them and we make a system of equations. I'll go back to black for this, right? And if we look at our equation above, right, we can sort of rewrite this. Now that we have our vectors, this goes to y, x is equal to the vector, well, before we write the vector, lambda times the vector 1, 1. Lambda is just some scalar in this case, some magnitude multiplier of the vector, right? Okay, so now we have that. Let's write our system of equations. So the equations for this is going to be y, which is our first component, equals lambda times our first component of this vector, right? Our second equation is going to be the second component equals lambda times the second component over here, which is just 1 as well. And then each of these just goes to, y equals lambda and x equals lambda. I'm not going to write that out. So if x equals lambda and y equals lambda, then it stands to reason that x equals y. All right. Now we've got 3 variables here, but we only have 2 original equations, right? We need a third equation to work with, and that's where we come back to the constraint function, which we said we needed to keep that 10 in there. It's important, right? So we use this original constraint function, which is just x plus y equals 10. And now we have 3 equations for 3 variables. And the 2 that we need to solve for is x and y. We don't really care about solving for lambda. Lambda is just a tool we use to get x and y. So x equals y, then we can substitute in, let's say, x for y in this equation right here, which gives us x plus x equals 10, which then means that 2x equals 10, which then means that x equals 5. All right, now if x equals 5, then we can plug that back into this equation that we have right here. And out of that, we have that y equals 5 as well. I'll go ahead and bring that down here. Okay, and these are that's our x and our y value, and those are the only x and y values that will satisfy both of these equations. That are critical points, that is. All right. Now we have an x component and a y component. We pair together all of the different x and y components that we found, and since we only found one of each, then that just gives us 1 point, and that point is 5, 5. Great. Now we have this point. What were you trying to find in the first place? Well, we were trying to find the maximum. We wanted to maximize this function of x and y. So let's see what the maximum is by plugging this point back into this function. Okay. Let's get rid of all this. Grab this back up here. Okay. Then we have f of 5, 5, right? Plugged it back into the f function, is equal to 5 times 5, which is just 25. All right. F of 5, 5 equals 25. That is your maximum. All right. Our second problem is to minimize a function f of x, y equals x squared minus y squared for the constraint x minus 2y equals negative 6. Okay, we're going to start out by getting our two different functions, and we can see right here, already written out in the form that we need it to, is our cost function, and our constraint function is right here, and we're going to rewrite that g of xy is equal to, let's see, x minus 2y equals negative 6. All right. First things first is to write the gradient functions for both of these. So the gradient of the f function is going to be equal to, gradient of the f function is going to be equal to partial derivative with respect to x for this first problem, which is just going to be 2x, and then partial derivative with respect to y is negative 2y. And then we have our gradient function for the other one, for our constraint function, rather, is just going to be 1 and negative 2. All right, now we know how we're going to have to set up our system of equations. So let's go ahead and write that out. Remember that the Lagrange equation goes like this. Delta f equals, not delta, what is that called? Labla or something like that. I'm not sure what the name is for the symbol. It looks like an upside down delta. But the gradient of f equals the Lagrange multiplier times the gradient of g. Okay, so let's go ahead and write out all of this in that format. We have 2x equals lambda times 1. Then we have negative 2y equals lambda times negative 2. All right, well, let's go ahead and write out these functions a little bit more simply. We have, let's say, we have 2x equals lambda, and we have y equals lambda. Okay. Now, we have 3 unknowns and 2 equations. So where do we get our third equation? We get our third equation from the constraint equation. So our constraint equation is x minus 2y equals negative 6. All right, now we can use this equation down here to solve for x or to solve for y. And then we can solve for whatever else. So first off, let's put x in terms of y with this set of equations here. Both of these are equal to lambda, so they're equal to each other, which gives us the equation, let's see, 2x equals y. Now we can go in here and substitute in, give me a second. So we can go in here and we can set 2x equal to y. And then we can use this substitution down here in the cost function to solve for either one. And I'm going to substitute in 2x for y and solve for x. So then we have, from that substitution, we have x minus 2 times 2x equals negative 6. And that's the same as saying that x minus 4x equals negative 6. All right, and now we can factor out the x, and we get that x times 1 minus 4, which is just negative 3, equals negative 6. And then negative 6 divided by negative 3 is just 2. So we have x equals 2. And now we can take this value, which is going to be one of our values, and we can plug it back in to find y, right? And if 2 times x equals y, then y equals 4. Y equals 4. Great, now we have our y value. And you'll notice in this particular case, we didn't even need to find lambda. You could go in and solve for lambda. Why would you? I mean, in this case, it's equal to y, so we know that lambda is 4, but it's not particularly relevant at this point. Okay, so now we have our x and y value. What do? We plug it back into our original function. So let's do that. And get rid of all this other stuff. And let's go f of 2, 4 is equal to 2 squared minus 4 squared. And let's see. What do we get out of that? We get that is equal to 4 minus 16, which is equal to negative 8. Excuse me, not negative 8. That's negative 12. All right. And that is your answer. Your answer is at point 2, negative 4. The minimum is negative 12. All right, now let's do a little bit difficult, or a little bit more difficult problem. This time we're going to do a function of 3 variables. As you know, the Lagrange multiplier can continue to scale to as many multipliers as you want, as many variables as you want it to. So this is a function of three variables. All right. So minimize f of x, y, z equals x squared plus y squared plus z squared. For the constraint x plus y plus z minus 6 equals 0. Now, the first thing that I like to do when given an equation like this where the constant is on the left side with all the variables, I like to just move it on over to the other side. So equals 6, right? Looks cleaner, works better. But yeah, just rearranging the terms so that the constant is on the other side. Okay, now we're going to write our equations. The first one, the cost function is given to us right here. The constraint function is this right here, which we're going to rewrite as g of x, y, z is equal to x plus y plus z equals 6. All right. Now let's do our Lagrange function. So for this, remember that the Lagrange function is going to come out with, or each gradient function in the Lagrange function is going to come out with 3 components: an x component, a y component, and a z component, right? So let's write out what that would look like. Look something like this. It has something here, 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 equals this times something here, here, and here. All right, now we need to figure out what our gradient functions are so that we can get each of these vectors. So the gradient function for f is going to be equal to, first component is going to be the derivative with respect to x, partial derivative. So we get 2x. Then partial derivative with respect to y for the second component. And for the third component, you probably guessed it, it's going to be the partial derivative of z. Right. And we're going to do the same thing for g. And that just comes out to what? 1, 1, 1. All right. So let's write our system of equations. We have 2x equals, well, 1 times lambda, which is just going to be lambda. 2y equals, here I can make my lambdas a little bit clearer, equals lambda. And 2z equals lambda. All right, well, from this, we can pretty much figure out that x equals y equals z in this certain system of equations. So you have x is equal to lambda over 2, right? So x equals, equals y equals z, which is equal to lambda over 2. That's bringing all of these equations together algebraically. And we have our one more equation, right, which is our constraint equation, which is that x plus y plus z is equal to 6. Well, that's really helpful, right? We can just go in and through substitution, we can just say that, say replace y and z with x, right? And then we get x plus x plus x equals 6, which is just equal to 3x, right? And then that goes to, x equals 2. And if x equals 2, then from this equation we have up here, then y equals 2 and z equals 2. And we don't really care what lambda is equal to. Okay. So x equals 2, y equals 2, and z equals 2. Now that we've found all of our values, what are we going to do? We're going to plug them back in to our original equation. Let's grab these values, bring them up here. And all of these values are going to go into the f function. We have 2, 2, 2, which is equal to 2 squared plus 2 squared plus 2 squared. Great. Now, let's see, that's 4 plus 4 plus 4, which is equal to 12. And that is your answer. F, the minimum takes place, the minimum of the intersection of these two functions takes place at 2, 2, 2, and it's equal to 12. And that's the answer. All right, so we went through 3 example problems. In our first example problem, we showed a very simple combination of two functions of two variables. And our second one, we did some slightly more complex functions of two variables. And our third one, we expanded to a function of three variables. Now, in all of these functions, we were already given what we were looking for. We were looking for a maximum or a minimum. And we only found one critical point for each of these. But in the following video, we're going to go into problems in which there are multiple critical points to choose from, and where we have to evaluate all of them. Oh, and by the way, if this video was helpful to you at all, I worked very hard to make it as clear and concise as possible. And it would mean a lot to me if you left a like and maybe a comment about what you liked and what you didn't like about these videos that I've made so far. All right. Thank you for watching.